Module 1, Lesson 1, Mathematical Model and Power Series. For this module, we'll be discussing mathematical models, accuracy and precision, the different types of errors involved in accuracy and precision, mathematical models that expresses infinitely differentiable and infinitely integrable functions like Taylor series and Maclaurin series expansion. A mathematical model is defined as a formulation or equation that expresses the essential features of a physical system or process in mathematical terms. In a very general sense, it can be represented as a functional relationship in the form of a dependent variable, which is equivalent to the function containing independent variables, parameters, and forcing functions, whereby your dependent variable is referred to as the characteristic that is usually reflects the behavior or state of the system. Your independent variables are the dimensions such as time, space, length, along with the system's behavior is being determined. Parameters are reflective of the system properties or composition, and forcing functions are external influences that eventually act upon the system. The actual mathematical expression can range from a simple algebraic relation to a large complicated sets of differential equations. As an example, Newton's formulated his second law of motion, which states that the time rate change of momentum of a body is equal to the resultant force acting on it. Its mathematical model is given by the equation F is equal to m times a, where F implies the net force, which is given in newtons or kilogram meter per second. Your m refers to mass, given in kilograms, and a happens to be your acceleration in meter per second squared. Hence, the mathematical model is an equation which usually falls after defining your given particular problem and then combining it with the theories that you've learned and the data that you have gathered. So mathematical model basically is a problem-solving tool that is usually used for computer statistics, different types of applications, which eventually yields numbered results or graphic results. And these particular results eventually have societal interfaces, which eventually includes scheduling, optimization, communication, public interaction, and then finally, the implementation of your particular solution. The equation has several characteristics that are typical of mathematical models of the physical world. They are, it describes a natural process or system in mathematical terms. It represents an idealization and simplification of reality. It yields reproducible results that can be used for predictive purposes. These particular mathematical models are often associated with calculated values that eventually includes what you call errors. When defining accuracy and precision, normally these errors are actually involved. Accuracy and precision for both measurements and calculations can be regarded and characterized based on the associated errors. Accuracy is referred to how closely your computed value or measured value agrees with your true value. And precision, on the other hand, refers to how closely individually computed measured values agree with each other. When you compare accuracy versus precision, on this particular graph, it shows that for letter A, you have a very low accuracy and very low precision values that are marked as dots on your respective bullseye. And then letter B shows you that increasing accuracy, however less precision, eventually yields to a more scattered values seen on this given bulls. And then on your letter C, you have increased precision, but less accuracy, which eventually shows that in your Bulls board, basically you'd end up with clustered values of computed values that are marked in dots, while letter D shows you values that are both accurate and precise. The different types of errors that are often associated with accuracy and precision arise from the use of approximations to represent exact mathematical operations and quantities. These are the computed type errors, which are the accuracy type errors, referred to as your absolute error, having the formula and a relative error having the formula. Approximate or precision type errors are very similar in terms of formulation when it comes to your accuracy type error, except that instead of values compared to your true or accepted value, values are being compared against one another. Hence, this would be the formula for your approximate absolute error, and this would be your formula for approximate relative error. There are also non-computed errors which often arise and affect values in your computation, which are referred to as the truncation error or the round-off error. Truncation implies chopping of your decimal places that are seemingly irrelevant on your calculation. However, when you do rounding off, you basically consider these respective values and round them off to the nearest decimal place value of significance in your calculation. Power series function. A power series in general are mathematical models that are used to represent infinitely integrable and infinitely differentiable function in a summation form. More or less, the respective form becomes more like a polynomial function. In general, this is your power series function, which is basically taken from your power series for linear differential equation, having that criteria that is near a regular singular point. Note that the coefficients C0, C1, C2 are the constant coefficients of your power series. And when this particular power series is expanded, you'd end up with this given form. And notice that this expanded form appears in a polynomial function form that is given by x minus a. This given polynomial, when expanded, eventually creates your polynomial. And the unknown variables here turns out to be your constants C0, C1, C2, all the way to Cn that eventually depicts your function. Note that these particular constants are different depending on your given particular function. Hence, these constants are the ones that you technically solve on your given power series. Now, to evaluate these constants on your given power series, the simplest way to do so is to evaluate the derivative of your expanded version of your function, which turns out to be like this, and continue on obtaining its derivative. So eventually, the second derivative will look like this. And your third derivative now would eventually end up like this, all the way to your nth derivative value. As seen on the differentiation of your power series, you'd end up with a particular pattern that allows you to evaluate now the constants, which looks like this. Hence, if you let a be equivalent to x, all those derivatives that eventually will have the function x minus a is simply reduced to 0. Hence, the first derivative at x, which is called your c1, is simply equivalent to the first derivative at a, while your function at x is noted to be function of a, since you assume a is equal to x. Now, the second derivative of your function, which denotes now 2c2, since the rest of the terms are considered 0, is now equivalent to the second derivative at a. Your third derivative of the function will now be equivalent to 3 times 2 times c3, since the rest of the terms are simply reduced to 0, or simply equivalent to the third derivative at a, since x is equal to a. Thus, you'd end up with the following relation for your constants to be like this. Hence, you can now solve constant c0 to be the function of x, which is equivalent to the function of a, c1 to be the first derivative of x over 1 factorial, or first derivative of a over 1 factorial, your c2 to be second derivative of x over 2 factorial, or the second derivative of a over 2 factorial, your c3 third derivative at x over 3 factorial, or third derivative at a over 3 factorial, all the way to your cn, bearing this recursive formula. Thus, when substituted onto your given expanded version of your power series, substituting each constants then gives us this respective power series, which is technically known as your Taylor series expansion. If we let then a be equivalent to 0, then the constants will be computed to be c0, which is the function of x, is now equivalent to f of a, which is now equivalent to f at 0, your function at 0, since a is simply equal to 0. Then your c1 becomes the first derivative at x over 1 factorial, which in this case becomes the first derivative at 0 over 1 factorial, since a is equal to 0. Your c2 becomes the second derivative at 0 over 2 factorial. Your c3 becomes the third derivative at 0 over 3 factorial. Having this recursive formula then, and substituting your constants to your expanded version of your power series, then gives us this result. Since a is 0, therefore we simply end up with x on our given polynomial function, which is then referred to now as your Maclaurin series expansion. The Taylor's theorem and its associated formula provides a means to predict the function at one point in terms of the function value and its derivative at another point. It's actually very useful in predicting errors that normally arise from the effect of nonlinearity and step sizes when applied in techniques like numerical differentiation and numerical integration. Such technique requires certain calculations that eventually allows you to approximate values. Hence, errors are often associated with them and are accumulated using this given theorem. Let's try to evaluate then this example. We're asked to determine the first 4 non-zero terms of your Taylor series expansion of this given function near a value of a equal to 0.5. So the solution basically involves in evaluating the constants c0 all the way to cn. Since we already know that a is equal to 0.5, we could simply expand the polynomial function x minus a. Hence, your f of x, or ln x plus 1, is simply equivalent to f of a, which is evaluated by simply replacing your x with 0.5, thus giving you the ln of 1.5, having a value of 0.4055 rounded off to 4 decimal places. Hence, your constant c0 is now equivalent to 0.4055. Your first derivative of your function carries the form ln u, therefore it's simply equivalent to 1 over u du, giving us a first derivative x value of 1 over x plus 1, or simply x plus 1 raised to negative 1. Thus, the first derivative at a gives us this solution, replacing your x with 0.5, hence giving us a first derivative at a value of 0.6667. Hence, your C1 is now equivalent to 0.6667 over 1 factorial, which gives us a constant C1 value of 0.6667. Your second derivative at A now is equivalent to negative 1 multiplied by x plus 1 raised to negative 2. Hence, your second derivative at A, substituting your 0.5 to your value x, gives us this solution with a value of negative 0.4444. Hence, your C2, which is negative 0.4444 divided by 2 factorial, is now equivalent to negative 0.2222. The third derivative at x is now equivalent to 2 times x plus 1 raised to negative 3. Thus, your third derivative at A gives you this solution, replacing x with 0.5. You'd end up with now the value 0.5926, and your C3 computed to be 0.5926 over 3 factorial, which is 0.0988. Thus, when these constants are substituted to your given particular Taylor series expansion, you'd end up with this following Taylor series function. Note that there are more terms involved in the series since the function is infinitely differentiable. However, we were simply asked for the first 4 non-zero terms of our given function, which eventually are these terms. Let's try to evaluate this time a Maclaurin series example. We are asked to determine here the first 4 terms of the Maclaurin series expansion of the given function f of x is equal to e raised to x. Note that on our Maclaurin series expansion, a is always assumed to be 0. Therefore, there is no need to mention that a is equal to 0. We then evaluate the constants with a being equal to 0. Thus, your function f of x is equal to e raised to x, which is your f of a being e raised to 0, or simply equal to 1. Thus, your C0, which is your f of a, is simply equal to 1. The first derivative of your function is also e raised to x. Thus, the first derivative at a, again, becomes e raised to 0, or simply equal to 1. Thus, your constant C1 is simply, again, equal to 1. Since if we divide 1 with 1 factorial, it's simply equal to 1. The second derivative at x is again e raised to x, which again gives us a second derivative at a e raised to 0, which is again equal to 1. However, your C2 now is equivalent to 1 all over 2 factorial, which is in this case equivalent to 1/2, or 0.5. And your third derivative at x is equivalent to e raised to x, and the third derivative at a is simply equal to e raised to 0 again, having a value of 1. Thus, you'd end up with the C3 equal to 1 all over 3 factorial, or 1 all over 6. Thus, if we substitute then these constants to your given particular Maclaurin series expansion, you would now end up with this given particular function. Note that the recursive formula shows us that the next succeeding term of your given sequence is simply x raised to 6 over 6 factorial. Due to that given particular recursive formula or pattern that we've seen on the terms of your Maclaurin series, you could easily predict the next succeeding terms of your given particular expansion. This ends the module.